This is presentation of linear regression with one regressor, or as we call it, simple linear regression. We often have a question that how can we explain the relationship between two variables? For example, how investment is influencing our profit, or how education is increasing our income, or how, as we exercise, our health is getting better, or how much the quantity of police force on the streets is reducing the crime. So behind every of these relationship, we can build up a mathematical model and explain that relationship quantitatively. This is why we are using linear regression with one regressors. This is the general equation. Here we call it simple linear regression because we have only one regressor, only one independent variable. In this example, it is x1. Later on we will develop a multiple regression model where we will have more than one independent variables. So y is actually dependent variable of the outcome. For example, this is our profit and x will be the investment. X is independent variable, or how we call it also regressor or predictor. Beta 1 is coefficient called slope, and it shows how y changes due to 1 unit change in x. So when we are changing x for 1 unit, what is the average change of our dependent variable y? Beta 0 is called, here it is called intercept or constant, and it shows the theoretical value of y when x is 0. For example, it will show the theoretical value of our profit if our investment is 0. yi is called error or residual and includes all other factors or variables that we didn't put in our model. So everything else that explains the variation of our data is here. The important thing to say is this is the population model. What does that mean? So population model explains the relationship in the entire population. We will never know the true value of this model because we never can collect all the data about all investments and all the profits, for example, in our country. What we can do, we can develop an estimate on the basis of the sample. So we will collect the data and create our sample, for example, with 100 units, 100 pairs of data of some investments and profits for example, in one country. And then we can estimate on the basis of the sample, we can estimate the values of the true model in the population. So please be careful when you see this notification. So when you have the hat, it means that this is actually the sample model or the estimate. For example, we will use the data about the class size. The question that we want to answer is, if class size goes down, how performance will be affected? So it is always very important to decide what will be the units of measures. For example, how to measure class performance. We will actually use test scores expressed in points. For every district, we will have the sample of 420 districts in the United States, in California districts. And for every district, we will have the average test scores of students in that district. On the other side, how to measure a class size. We can count the number of students, for example, but here we will actually express this class size as a student-teacher ratio. How many students on average goes onto one teacher in every district. So we are now exploring the influence of the class size on the test scores. And this will be our estimated model. So test score will be calculated on the basis of the coefficients beta 0 hat and beta 1 hat, and we will in the model put the student-teacher ratio, the data that we get from our sample. So beta 1 will show us the average change of test scores if we increase the student-teacher ratio by 1. We are actually interested in two things. It is prediction and it is the size of the effect. Prediction means that we want to see what will be the test scores for a certain size of the class, while the size of the effects means that we define how strong is the relationship and how big is the relationship between student-teacher ratio on one side and test scores. So there is 420 districts in California. There are too many differences between the two districts, these 420 districts, because some are the richer, some are the poorer, some are, for example, have much more students than the others. Some have immigrants, some have less immigrants, and so on. It means that when we calculate the model, it shows the relationship on average. So our model is average across the population of districts. And every time when you're explaining the beta coefficients, beta 1 coefficients, specifically, you need to say that this is the change on average. It doesn't mean that beta 1 will be the same for every district in California. It is on average for 420 districts. Also, we can add more variables in our model so that we can put into account those different differences between districts. For example, the size of the income, average income in every district, demographics, for example, I don't know, number of immigrants, teachers' wage, and so on and so on. But at the moment, we are only exploring the relationship between size, class size, student-teacher ratio, and the test scores. While the other factors, we will later on develop some multivariate models where we will add some factors. So this is our model in population, and we want to estimate it. In order to estimate beta 0 and beta 1, we will develop estimated model. On the picture, you see with these red crosses, these are our original data for 420 districts. For example, in some of the districts, student-teacher ratio is somewhere below 20, let's say 90, and the test score for that district is somewhere around 605 test points. Already you have the blue line here. These are actually the values of our model. So on the basis of our linear model, we actually estimated the regression line, and it goes down, which means as the class size is going bigger and bigger, test scores are lower and lower. Here are actually the values of our beta coefficients. We will take care about it later on. So the question is, how do we get the values of beta 0 hat and beta 1 hat? What is the mathematical background for this? We are calculating them on the basis of the ordinary least square technique. So we will get ordinary least square estimators in our model. The idea is to find the line that has minimum distance from all the points. So if these black dots are our original data and we implement our model on the basis of the equation, it must be in the place that minimizes the distances between these dots and the regression line. It cannot be here or it cannot be there. It must be somewhere in the middle in order for those distances to be as small as possible. So we are minimizing the sum of the squared errors. Okay. How we are minimizing it? So this is our goal, that our differences between our original data and our model squared is minimized, is minimum. We actually want to minimize the residuals. These differences, we are calling them residuals. So these red lines are actually showing the distance between every dot and the regression line, and these are called residuals. So difference between original data, dots, and theoretical data, or the model, expressed here as a straight line. So this expression here is actually same as this expression here. We want to minimize UI hat squared. Why do we square these residuals? Well, first residual is positive, second one is negative, third one is positive, fourth one is negative, and so on. If we add them up, in sum it will be zero, it will be null. So in order for these negative distances to be positive, we need to square them. This is why we need to square residuals in order to minimize them. So these are actually the formula to calculate beta 1 hat and beta 0 hat. So it is really simple. If you have original data about your independent variable x and values for your dependent variable y, you can calculate x bar, you can calculate y bar, so averages of your independent and dependent variables, and then you can calculate beta 1. On the basis of beta 1 and average values for x and y, you can calculate beta 0 hat. So if you do it on the paper, it goes like this. You will create a table. You have the values of your dependent variable, your independent variable. You have the averages of these variables, and then you will calculate step by step every part of this equation here, and then you can calculate beta 1 hat and beta 0 hat. Because of PowerPoint, you don't see here it is x bar, this is y bar, this is also x bar because we need it here, and also this is y hat. So on the basis of the beta 0 and beta 1, we can calculate theoretical values of y hat, and then we can draw the straight line like here on our picture. So if you put these values for x, 2, 4, 4, 2, into our equation that we calculated, for example, into equation here, you will calculate the values. This is unknown, we don't know this. So you will get the values for y hat, and then you can put them here in the table. Why we use OLS estimator and not some other? Because it is unbiased and consistent. What means consistent? As the number of data points used increases indefinitely, we are getting approximately same results, leading us to the true value of beta in the population. So as our sample is growing, for example, for 100 to 200, 300, 550, and so on, we will getting a little bit different but similar results of beta 1 and beta 0, and we will going straight to the true value of beta in the population. For example, if the population is 1000, then if we enter 1000 data in our model, we will get the true value of beta. But it is never happened. We need to decide and estimate it on the basis of the sample size of 100, for example. What we want to achieve is that our model must be blue. Blue means best linear unbiased estimator. Now we will explain every part of it. So best actually means the smallest variance. So you can use different methods for calculating your estimates. It doesn't have to be OLS, but then you will get different characteristics of these estimators. So smallest variance means most efficient among particular class of unbiased estimators. For example, if we have estimator beta hat and we have estimator beta tilde calculated on the basis of some other model, which of these two is better? So the gray line shows the distribution of beta tilde, and it obviously has the bigger variations. So variance of beta tilde is higher than variance of beta hat. This is distribution of beta hat. For example, if you have a chance to 100 times, calculate the sample size of 100, and then calculate different values of beta, you will get this distribution. So obviously, on the basis of this graph, that smaller variance is for beta hat, and this method is better. This is why we are using OLS, because it gives us the smallest variance of our beta estimator. Second, linear, best linear unbiased estimator. Linear means because we are exploring linear relationship, we will get the straight line among our data. This is why it's called linear. Unbiased because it is on the true value of the parameter in the population. For example, you see here in general sense where the true parameter is. So this is its distribution. And if we are using the wrong method, the estimate that is biased, distribution of our estimator will be, for example, here. It won't be on the true value of the true parameter in the population. Therefore, if we have the true value of beta here, and if we compare two estimates, beta 1 hat and beta 2 hat, it is obvious that beta 2 hat is biased. It is moved to the right. But beta 1 hat is unbiased because it is on average on the true value of beta in the population. So this is what we get if we are using OLS method, ordinary least squares. You will see that some assumption must be satisfied, and then if all these assumptions are satisfied, you will get unbiased estimator.